Today I would like to talk about our Charpy Impact Tester and how it relates to the math we use every day in our industry. What the Charpy Impact Tester is it's a machine that's used for measuring the actual impact toughness of materials. Materials all behave differently at different temperatures. Typically with these specimens, we'll cool the specimens off to whatever the contract requires, 20 below, 40 below, and determine how much impact or foot-pounds that physical material can handle at a decreased temperature. We specifically want it to break in that exact location. So the specimen itself is a 55 millimeter long specimen that has a groove in it that is a machined groove that is 2 millimeters deep, and it has a 1/4 of a millimeter radius down in the bottom of it. The specimen is then placed with a set of tongs designed for the Charpy Impact Tester, so the actual notch is facing outward from the impact. The sample itself, each one is identical. Typically we'll do 3 to 5 specimens and then take an average of those specimens and then determine the foot-pounds of that actual material itself. In our industry, it relates directly to, we have products that shipping industry, cranes are the environment that those materials are going to be under load in. Typically those temperatures in the ocean, you can get 40, 50 below wind chills. When we're talking about cranes, you get to northern Alberta, you're looking at a high for 55 below some days. Those materials have to behave and perform in those temperatures. And that's what we're going to talk about today. The Charpy Impact machine is designed to physically measure foot-pounds of force absorbed. In this situation, we have no specimen located inside the jaws. The machine is set ready for swing. So as soon as I release that hammer, this machine should read 0 because 0 foot-pounds of energy were absorbed without a specimen. Typically the specimens are chilled to a prescribed temperature. Depending on the contract documents, that stipulates what that temperature needs to be. In this case, we have a problem. Our contract documents stipulate the temperature in Fahrenheit, but our machine reads in Celsius, so we're going to have to do some converting. Our industry standard typically is -40 or -20 degrees Fahrenheit is commonly what we have to chill our specimens to. When it's at -40 Fahrenheit, that's a good one because -40 Celsius and -40 Fahrenheit are the same. We have no math to do. Our situation involved -20 degrees Fahrenheit and we need to convert it to Celsius. The equation for that is, to come to a Celsius answer, we need Fahrenheit -32 divided by 1.8. Our equation would be written out as -20 degrees minus 32 divided by 1.8, giving us -52 divided by 1.8, making our answer in Celsius -28.8889 degrees Celsius.